Welcome to SCA's webinar today with Jamie Woolsey and Sarah Kallner on Steer Without Fear, Practical Geosteering Applications. Jamie and Sarah teach geosteering, best practices, pitfalls, and applied solutions for SCA. It will be offered in Houston, Texas on April 10th through 11th and October 30th through 31st this year. Before we start today's webinar, we'd like to ask a few questions about the demographics of the audience. So I'm going to launch the first poll, and this is a poll, what is your primary discipline? So you should see that poll. People are starting to vote. Looks like we have a pretty good spread between the petroleum engineers and the geoscientists. Okay, most of you have voted now, so I'll go ahead and close that poll and share the results. We have 71% in geoscience, 21% in petroleum engineering, and 7% in petrophysics. So let me share the next polling question. How many years of experience full-time do you have in the upstream oil and gas industry? Looks like we have a pretty widespread in our demographics. The answers are coming in now. Looks like most of you have voted, so I'll go ahead and share the results. We have 44% in the 11 to 20 year bracket, followed by 25% each in over 30 years and 1 to 10 years, and then 6% in the 21 to 30 year group. So I'm going to close that. And before I do the introductions, I'd like to remind the audience today that you are muted, but you can ask questions during the presentation using the GoToWebinar question feature, and we'll cover the Q&A at the end of the presentation, and you will be anonymous. So the webinar today is Steer Without Fear, Practical Geosteering Applications. And Jamie Woolsey is one of our speakers today. She's also an instructor with the class of a similar name, and she has 18 years of experience in both unconventional and conventional in various basins throughout the United States. And she received both her BS and MS in geology from the University of Arkansas, where she is also an adjunct professor. She's president of the APG Mid-Continent section. Sarah Kallner is a consulting geologist based in Houston, Texas. Her experience includes work at Conoco, Marathon, and Exxon. She has also worked quite a few basins in the United States, including Gulf of Mexico. She has a BS from TCU and an MS from OSU. So here is the description of the course that Jamie and Sarah teach. It'll be offered twice in Houston, Texas in the spring and the fall. And this is an in-person course. We can also arrange to have this course offered at your office if that's more convenient. So join SCA at the CCUS conference that's organized by SPE, APG, and SEG. That's next month in April, at the end of the month, at the University of Houston Hilton. The next free webinar that's coming up from SCA is Drs. Larry Lake and Jerry Jensen on why a no geology model helps us understand geology. That will be Thursday, May 11th. And we have some upcoming live online classes that are offered in half-day segments. So CCUS from a geological perspective is taught by Dr. Steve Sonnenberg, April 24 through 27. And CCUS from an engineering perspective is taught by Drs. Christine Economides and Demetrius Hazignatou. Those dates are May 15th through 19th. And of course, SCA training courses can be taught in your location if you prefer an in-house class. So contact us for that information. And look to SCA for, in addition to your training needs, any consulting, projects and studies, and direct hire opportunities. So I'm going to change the presenting rights to Jamie, and it's all yours.
Okay. All right, well, thank you everyone for joining us today. And then thanks to SCA for allowing Sarah and I to present today. So since there are a couple other geosteering webinars out on the SCA website, we've sort of designed this presentation or webinar so that we don't have much overlap.
So Jamie, I'm not seeing your slides yet.
Oh, sorry. Did I? Oh, there we go.
Now we see them.
Okay.
Great.
All right. Okay. So what we're going to talk about today is just some obviously overview of geosteering, what it is, why we do it, the importance of pre-drill geologic models, and then data quality concerns that we often encounter and how they affect your interpretation. And then we'll give some practical tips for use in the curve and the lateral that you should be able to walk away today and put to use. I do want to credit Raymond Woodward, who previously taught this class for many years. Raymond, I started working with Raymond over 10 years ago at BHL Consulting, where he is one of the original founders of. And he basically has built the foundation for this presentation and also helped with a number of the slides. So a little bit about the history of horizontal drilling, just because I find it sort of entertaining. So first off, please note that a deviated or a directional well is not a horizontal well. So deviated wells have a slant, but they don't actually go fully horizontal. And deviated wells are usually drilled to avoid an obstruction or avoid an obstruction such as, say, a river or lake, or when you're doing platform drilling or pad drilling. The first horizontal well was recorded as being drilled in 1929 in Texas. And then there was one in 1944 in Pennsylvania. But most commonly, the Austin Chalk play is where horizontal drilling really started to take off. The Austin Chalk is a naturally fractured reservoir, so it didn't require the massive frac jobs that we do today. In 2003, the invent of hydraulic fracturing, which is credited to George Mitchell and the Barnett Shale, is where everything really started to take off. And so the realization now is that we can put a big hydraulic frac on low perm, low porosity source rocks to make them economic. So of course the benefits are primarily the economics. With the horizontal well, you get much more exposure to the rock and hence the hydrocarbons. And it makes many places economic that would not be economic if they were drilled vertically. And then the environmental impact, talk about the upside to it. You know, when you can drill one horizontal well as opposed to several vertical wells, you really eliminate your surface impact. And then now we do pad drilling. So you may have 4 to 8 wells drilled upon one pad that really helps to lessen the impact we see at the surface level. All right, so this is the U.S. rig count, which starts in 1991. This data is taken from Baker Hughes. I found it on a website, ycharts.com. The data is accurate though. So their data begins in 1991 and goes through this month of 2003. Horizontals are the purple line, so you can see where the horizontals and the verticals and directionals really start to change. These inflection points, of course, represent drops in oil prices. So in 1991, 9% of all wells being drilled in the US were horizontal wells. In April of 2010 is when horizontals take over the majority of wells being drilled, so 51%. And then in this month, March of 2003, we're at 93% of wells being drilled now are horizontal wells. Just to add a couple other Reference points, the max horizontal rigs we had drilling was in the fourth quarter of 2015. That was 1,372 rigs, horizontal rigs, and today we're at 692. All right, so what is geosteering? Geosteering provides a highly detailed foot-by-foot look at what's going on in the subsurface compared to the relatively low detail resolution of maps and seismics. So the point here is that, when you don't, with geosteering, we see everything on a foot-by-foot basis, as opposed to having two, offset wells that you're trying to interpolate what's happening in between. And that's hard to resolve even with seismic at times. So it can't resolve down to the foot-by-foot resolution that you need to see in geosteering. Our goal is always to determine the stratigraphic position and use all available data to deliver the most economic well possible. Geosteering is not intended to prove the prove the pre-drill model, execute the directional plan as stated, and it's not to only drill or always drill the lateral at 100% in target. Of course, we all want our pre-drill model to be correct, but we have to remove any biases during our geosteering. And trying to stay 100% in zone can often lead to incorrect interpretations and severe doglegs if that is the only goal. So severe doglegs can occur as you're about to exit the target window or as you're trying to get back into it. And then the rear view mirror, so that's my pup there. I chose that picture, but it's a good analogy to what we're doing. So we never see what's in front of us, we only see what's behind us. And in fact, because the MWD tool is actually about 45 to 60 feet behind the bit, depending on your assembly, we also have a blind spot in there. So in this example, I wouldn't even be able to see my sweet little pup there. We'd be looking at a point back here, 45 to 60 feet behind the bit. And what we haven't seen is that the road deviates, and in fact, I've probably just driven off into the ditch. So just keep that in mind. The accuracy of your interpretation depends on how well you understand the depositional and the structural setting. So is this a deltaic environment? Are these channel sands? Is this a part of the Permian where you have prolific lime debris flows? Is this the Utica Shale, which is in eastern Ohio, is some of the most pancake geology that I've ever seen in the subsurface. What's your structural setting? Do you expect to see faults? And do you expect them to be upthrown or downthrown in the direction that you're drilling? And representative type logs, that's very important because any variation in stratigraphy or thickness can cause your apparent formation dip to be skewed. And it can be misleading when you're trying to land the well and drill the lateral. So, do you know or do you think this is actual and this is real? Just remember, when you start off, you have to sort of interpolate what is happening between your hard data points. And then small scale, just know that things you see on a small scale, they're unexpected, but they're real because you're looking at stuff on a foot-by-foot scale. These variations may be real and they may be exaggerated, but the overall picture needs to match your known context. So know your pre-drill geology. And then survey accuracy and data quality also affect the accuracy of your interpretation. Just a quick example here with some generic photos. This is sort of your layer cake geology. This is what is obvious, and this is what is actually seen. So this just points out some facies changes, some variability in the stratigraphy. So if you sort of imagine you're drilling along this bed, and then all of a sudden you hit different rock, and how do you determine if that's a fault or if it's simply a facies change? And this is where knowing your geologic model and knowledge of the setting comes in very handy. And of course, it's always fair to say, I need more data to determine. And that's pretty much, that's happens very often, and no one likes to hear that. This is a very simplified pre-drill model where you have two vertical wells, well A and well B. You have the target, which is a 20-foot target section. Overall, the dip is about 91 degrees up dip, or 1 degree up dip. The distance between these two is about a mile. So with this being the only data you have, this is the only interpretation that you can really come up with, is that dip is constant from well A to well B. Anything else that you try to come up with would just simply be guesswork. But this is what we don't see, because the resolution just isn't there to see with pre-drill data. So this could possibly be the scenario where overall the dip is up dip, but you have a lag in here. But from point A to point B, your average overall formation dip still remains the same. And of course, then faulting could also be a possible interpretation, because this would be a small fault. Remember that target interval is only 20 feet thick. So 10 to 20 foot faulting is below resolution of even seismic data. So, I think the point to make here is just know that a lot is happening in between point A and point B that you're not able to see prior to steering the well. So just quick point out some of the terminology, just so we're all understanding how to read these plots and what we're doing. Of course, this is your 0 feet vertical section. Your vertical section is actually a horizontal distance along from point 0 feet BS along the lateral. Here's your kickoff point. This is where you build the curve and you land the curve. Directly underneath the, at 0 feet vertical section, or directly underneath the KB, is what we refer to as TVT depth, which would be true vertical thickness, or KB TVD is also been a term for that. And that kind of comes into play later when you're comparing to type logs. And then vertical section azimuth, I'll show you that better on the next image, but it's basically a plane in the direction that you're drilling. And of course, just remember that formation dip is what the rock is doing, and inclination is what the bit is doing. So sometimes we have to make sure, careful what we say to drillers and how we say it. All right, so just so we have a better understanding of the critical data, there are really only 3 survey data points that are needed: measured depth, inclination, and azimuth. And then everything else is always calculated based on those 3 values. And so your directional driller would have a program that he puts his MD, inc, and azimuth into that then calculates all the other values. So that will calculate TVD, your vertical section, your east, west, and north-south offsets. We take those same 3 data points and we put them into our geosteering software, and our software will calculate those as well. So they don't always come out perfectly matching, and there's always a rounding error in there that leads to some interpolation errors. But those are the 3 things. Everything else, almost every fact of geosteering rests upon the MD, the inc, and the azimuth. And the calculations themselves can and often do generate survey errors, and we'll touch on that momentarily. Just to point out, so inclination and dip are expressed by directional industry standards. So the drillers have determined that formation dip should be referenced at 90 degrees, which would be flat, and then deviate from that. So 91 degrees is 1 degree up dip, 85 degrees would be 5 degrees down dip. So we adjust to their liking there. So this vertical section azimuth, okay, it's important that you're using the correct vertical section azimuth, and all that is the overall direction that you want to be drilling. So this is your well bore of the well that's already been drilled. The vertical section azimuth was 180 degrees. That's just the overall direction that they wanted this lateral to go. It does not change along the lateral. You can usually find it. So that's a value that we would have to input into our geosteering software. So we always want to make sure that we're matching and we have the correct vertical section azimuth as the directional driller does, so that our numbers come up correctly. You can usually find this in the survey spreadsheet header that they send out. If it's not listed somewhere, you definitely need to contact them and find out what they're using and confirm it's correct. Just a little note that sometimes the vertical section azimuth that they use when they're drilling the vertical portion of the hole could be different from the lateral vertical section azimuth. So once you get that first survey, as you're getting picked off to start drilling your curve, you just always want to double check that your numbers match the directional company's numbers. All right, positional uncertainty. This is a slide. This is a slide taken from BHL Consulting's website. There are a number of factors that go into how positional uncertainty can affect your interpretation. And basically what it is that there's a cone of uncertainty around your wellbore. And that uncertainty increases the further out into the lateral that you get. It stems from a number of different things. I'm not going to spend time on it because Raymond actually has like a 1-hour webinar just, almost solely dedicated to the explanation of this. But the point is that there's quite a bit of uncertainty in the surveys that are being calculated. So some of the data quality issues that we have, pipe tally errors. So most often these occur right after drilling out of intermediate casing, or sometimes if you switch directional companies and you run one off and another one comes out and they tie into the existing data, there can be an error there sometimes. These pipe tally errors usually occur in measured depth errors of 31 feet or 93 feet, so either a joint or a stand. And so this just recently happened where we were off by a complete stand, and so the prod was coming in 100 feet off. The geologist was very concerned, so he had the directional driller do a recount. They actually had to send somebody out to count all the pipe that was on location and subtract it from what should be left in the hole to determine that they were actually off by a complete stand. Then errors with MWD data. Of course, we have baseline shifts between tools. So one tool could be reading slightly, it was miscalibrated before it was put in the hole, and it could be reading slightly higher or lower. Gamma ray shifts that happen within one tool are also possible. Those can be affected by downhole temperature. And so this has become a common issue recently, where once you get over the 350 degrees in the hole, that high temperature starts to cause your gamma ray to start reading increasingly hotter or higher. And then gamma drift, which I have an example of, and all this relates back to the importance of doing a relog and trip annotations in all your interpretations. So a relog is when they pull it, they pull out of the hole, they change the bottom hole assembly, including the MWD tool. They calibrate it at surface, they put it back in the hole, and they'll pick a portion to relog as they're tripping back in the hole. And so this is an example. The green is what was originally read by the first tool, and the blue is the relog as they come back in the hole. Okay, that one's good. You can see that, and you'll get this before they start drilling, so you know what to expect. Here, the green is what the previous tool read. The red is the relog. We have an API shift of about 20 units. That's fine. As long as we know that it's there, we can deal with it afterwards. And then this is an example of probably a relog that was ran much too fast, too quick while they were tripping in the hole. You don't get the counts that you need there. And also poor choice of a section to relog. There's just an extreme amount of variability in there that would be hard to read at the rate that they're tripping back in the hole. So here's an example of a single tool gamma drip. So this is all within one tool. This is the gamma ray along the lateral. And you'll note that there is chatter or spikiness in this that happens frequently, and there's an option in most software to sort of despike the data or average the data, which we try to never do. We try to never alter the data unless it's just uncorrelatable otherwise. But the point here is that this tool made 4 passes through the same section. The blue is the first pass down, and then green starts to read higher, and then your light blue higher, and then the red as they're coming back up even higher. So it got incrementally higher with what we call a drifting gamma calibration. And this is, again, a real example. So this, just to reiterate, this is what a tool shift would look like. So you would have this data, they would trip, change tools, and come back out, and there would be this abrupt shift. That shift is a classic fault signature in a horizontal well. Okay. So when you see something like that, you would automatically go to fault. But and then once that happens, you know there's a trip. How often do you trip right at a fault as you encountered a fault? But it has happened. But so you drill, and you've got pretty monotonous data here and on the other side. And the problem here is if you don't have a relog, you could be drilling hundreds of feet before you get into a signature on the gamma ray that you're able to confidently say, okay, this is a gamma shift and not a fault. And if you simply did the relog, this wouldn't be of concern here. This is just a diagram to show you how the impact of a non-representative type curve can affect your formation depth, particularly in the curve. So at short vertical section distances, any changes in thickness or stratigraphy is going to be reflected as a incorrect formation dip. Okay. So at 50 feet VS, just as an example, a 10-foot change drives a 10-foot change in section, stratigraphy, shift, however you want to put it, would be 11.5, would calculate an 11.5 degree dip, which would take your, say your progged formation dip was 90 degrees flat. This now takes you to a 101.5 formation dip, which is obviously not correct. Now, once you get out to about 500 feet vertical section, a 10-foot change only results in a 1.15 change in calculated dip. So we just have to use caution when we're adjusting formation dip while building the curve. And this is really the primary reason why it's not uncommon to see geosteering interpretations with extreme dips while they're building the curve. This is, however, not our preferred method. As an example of this, this section here was taken and adjusted. We adjusted the formation dip to 81.8 to match the type log, which is really just a thickness variation. But if you put this interpretation out as you're drilling, so you would only be at this point, then your directional driller looks at that and he projects the target out at the dip that you're reporting. That now lowers your projected landing target at projecting landed by 35 feet. So just always be very cautious when doing that. The recommendation, our recommendation, is to handle them essentially as small faults, false faults. They obviously are not faults, but they're just changes in thickness variability. And by keeping the dip of each cell consistent with what your anticipated formation dip or your prog formation dip is, ensures that you're always projecting your landing out at the appropriate dip. And I apologize, I should have put this in earlier. So this is an example, just explaining how to read these plots. Of course, this is your wellbore, this is your target interval. These are the segments along the lateral, the gamma ray segments that you use to interpolate. So we can look at this gold segment here, and we see that it's this portion in the type log. Okay, but this is my next example. So when you're drilling the curve, how do you tell if you have stratigraphic variation or just thickness variation with the type log? This is an example from the Austin chalk. As we're drilling along, the section starts to shift up on us, and then as we continue to drill, it shifts back down on us. So the prog formation dip at landing is supposed to be 91.4 degrees. So just to look at a section, and specifically what I'm talking about here, is we've taken this red section, we've shown it here, and we've just shifted it to make it match the type log. We've shifted it down 5 feet, which results in a 5-foot shift up in your DVD view. And same thing, we had another shift before we came to the next segment, and so there was another shift there. The important thing here is these are not faults, it's not missing section, these are just variation either in stratigraphy or thickness with the type log. And then if we zoom in and look at this a little closer, and we see how we've had to adjust this section, segment it apart. And look, you could get real tedious and put all the sections and segments and cells you wanted in here, but you really just need enough so you can visually see what's happening. So everything's pretty good match. We've done a lot of shifting up and some shifting down, but if we calculate, and I've shown these as faults simply to give you the offset on each one of these. And if we calculate all of those together, we find that it only comes out to a difference of 3 feet TBD. And then if we look at what is the dip, if we just take a constant dip from the first cell to the last cell, that dip would be 91.6 degrees. Our prog dip was 91.4 degrees, so that is very close and within the realm of the expected scenario there. So from that, we can determine that this is just stratigraphic variation, right? So you had some thinning compared to the type log, and then you have some thickening. So the section sort of evens itself out. And then another example, this is East Texas. The prog formation dip is 91 degrees. You can see as we're building the curve, we take several steps up, step up. This would, we'll look at here, we'll look at it a little closer. We put values to those. These are within just 1 to 4 foot increments. But when you add them all up, it comes out to 35 feet TBD of thinning compared to the type log, okay, overall. So when you look at that, you can tell that this constant shift is that the overall package is thinning all the way throughout, not just in one portion here and one portion there, but overall, all throughout the section there, we have thinning. If we're stepping down, then we would know that our section is thicker compared to the type log. And if another way to test that is we do the dip from the first cell to the last cell. This is this would be at 100 degrees, which is obviously does not match the geologic model. So we can conclude that this is just thickness variation with the type log. Pseudo logs or KBTVD logs, just depending on what software you use. This is basically when you use a existing, you use the curved portion of a drilled lateral, and then you take it and make it vertical, a KBTVD log or a pseudo log, so that you can use it to steer another well. So maybe your second well on the pad. The best scenario for using pseudologs is where there is relatively little formation dip and where you have confidence in your formation dip. Okay, so what you want to do is you want to take one large cell. The gray here is the type log, the original type log that was used to steer this well. We take the curved portion, we put it at one big cell. We put it at 89.5 degrees because that's what the overall or the dip was at landing. And then we create that pseudolog. However, any change in dip, if we put this dip at 90 degrees, it's going to result in a expanded or thinner pseudolog section. So we just recommend that you always use caution with those. And to be accurate, you should also project or also create pseudos at varying formation dips. So you might do it at 89.5 and 90 degrees, just to be certain. I did this example at both of those, and a 0.5 degree difference resulted in 6 feet TBD difference in the target interval. Just know that, most of your errors are going to occur, at the landing or where you have the most inclination in the wellbore. So the most ideal situation for these is when you have a deeper target that you've drilled, say a Wolfcamp C well, and you use that as a pseudo to drill a Wolfcamp A well, where the target would have had very little inclination to skew the pseudolog. Regardless, though, always use with caution and always have a backup vertical log. This is just sort of a quick example to walk you through a couple scenarios here. We're landing a well. We're at 45 degrees in the curve. Here's our landing target. That's what the driller is aiming for. This red is the center of our target. We're correlating to a type log that's about 4 miles away. So the target line at 45 degrees in the curve is projecting to be about 18 feet below center of target, which puts us landing at the very base of the target. So then you have to ask the question, should you raise the landing? And sometimes we get a engineer who will say we cannot, no changes past 50 degrees or something like that. So no changes past 60 degrees. So this is kind of a critical time to decide what you want to do. So just to be safe and to double check and use all available data, we create a pseudo. We compare that. That pseudo is an offset lateral on the pad. It's about 600 feet away. And with that pseudo, our target line is now projecting to be 1 foot below center of target. So we can have some confidence, and maybe in this case, we'd go ahead and hold off on making any target changes. So let's see how that ends up being once we land the curve. So again, this is using the type log that's a couple miles away, and we see a little bit of shifting. Again, thickness variation with the type log. The end result is that our target line ends up being just 6 feet below center of target, as opposed to 18 feet. And then if we look at it with the pseudo log, we also see a little bit of shifting there. It's not as much. We have about 6 feet of shifting. So at landing point, the target used with the pseudolog, the correlation with the pseudolog, the target line is 5 feet above center of target. So when we started out at 45 degrees, there was 17 feet of variation between the type log and the pseudolog. Now that we've landed the well, there's only about 11 feet of difference. But it can be, it could be the difference in landing in target and out of target. So the point here is that if you have the possibility to use a pseudolog and it's a good scenario, then you want to use that and you want to take full advantage of that. You want to use all available data, but just with caution. And then that sort of wraps up my portion. Sarah's going to talk to you about drilling the lateral, some of the tips and tricks that we use there. This is just a comical relief slide to make our transition. So, and it seems, I'm sure we all agree, it seems fairly appropriate. So. Okay, Sarah?
Okay. Yeah. All right. All right. Did you give me control or you got it? Okay. So pretty much, um, we've landed the curve. What now? What's the number one goal? Stay in the target. Simple enough, but there's a caveat to that when it's best suited to the situation. So, um, what we can do, a thing that we need to do is we need to ask questions, communicate preemptively. Geosteering, a lot of time, you're the middleman, you're the connection between the rig and the office. You know, you're working with the company man and your day and your night hours of your drill. You're keeping everyone kind of on a continuous loop. We need to also, I want you to be observing the slides. You can see that by looking at your ROP curve and monitoring your trips. Jamie kind of touched on that. And revising your target only when necessary. We don't want to get into crazy target changes that are unnecessary and micro steering, and that kind of leads into hedging our target changes in favor of the pre-drill model. What they probably have, and for good reason, dogleg goals and anti-collision and what's going to be best for completions later on the road. We're just one piece of the equation. And also be aware of our limitations in the pre-drill model. By pre-drill geology, I mean the decision to drill, your well placement, your target selection, your tool selection, interpretive bias. The pre-drill data almost never resolves the fine scales that are important to the geosteering operation, which spatial density way bigger than way higher in your horizontal hole. So just a couple helpful tips, things to keep in your back pocket when you're steering your own lateral. I always go with the 1.75 rule. That's a fast one that's commonly used for every degree drilling versus the formation dip. The difference between your drilling ink and your formation, expect to move about 1.75 feet per every 100 feet. And we have some examples of just to make that more clear. And just a fun one we like to say, when in doubt, stretch it out. So you get the next piece of data, you append to the previous step. Okay, so let's stretch it up, let's stretch it down, let's see where it fits. That makes geologic sense. The rules of averages, we don't want to get hung up on the little dip of each cell. Ever interpret it. I want to think about overall average, and this kind of leads us. We're going to have a slide on this too. It applies the same to surveys coming in, especially if you're getting them for a mud motor and RSS. Mud motor can, the RSS typically they can hold inclination a little bit better, and you're going to have a smoother of a time in your lateral. And then the one big cell rule, or not rule, but it's good to see where your wraps are to get your average dip, and those will be pretty apparent. If you have a large section of data, that's all one dip. And then always read your mud logs, be aware of the gas, don't let it drive your interpretations, but your sample and your gas should help you. Don't ignore it. And let's see, be friendly with your MWDs. It's a soft skill, but it's really important because a lot of data issues that are in previous webinars, there are things that come up like telemetry, how the data is coming to the surface, your degradation, your bandwidth, how the gaps are being filled in your gamma. And Jamie said temperature. To high temperature, you can have a slowly increasing baseline or mid-run failure. The gamma tools can be calibrated not so great, and they're not always quality controlled. So it's good to be able to make a phone call to your MWD out there and have candid, nice conversations with them. And then if all else fails, just blame drilling. I'm mostly kidding. Raymond Woodward has a great webinar on understanding your sources of horizontal position uncertainty and data issues. He touches on survey errors, and a lot of times the surveys are edited on location, your TBD uncertainty, BHA sag, rotating versus sliding, stuff like that. So here is our quick look. You don't have to do crazy math like the woman in this photo. Just so for every difference in change, 1.75 feet, you're going to move up and down between your drilling ink and your interpreted formation dip. So I have two examples if you want to do it all together. So your formation dip here is 92, your drilling inclination is 93. How far are you going to move? So there's 1 degree of difference between your 92 and your 93 times your 1.75. So in 300 feet times 3, you will move up 5 feet. And then our second example, same concept. Now your formation dip is 89 and your drilling inclination is 85. So we know we're going to move down. That would be very bad, but it's an exaggerated example, but we're drilling much beneath formation dip. They want to know how far are we going to move down? When are we going to be in trouble? So in 200 feet, you're going to move down 14 feet. So just keep that in your back pocket. The when in doubt, stretch it out. Here we go. So here we got a few surveys. We appended to the last cell of data. We put it at the same dip. Looks a little suspect. So let's go to the next slide and see. Let's just stretch it down. So that's not bad. It looks okay. The shape matches, but remember in gamma, we're trying to look at shape and we want to keep magnitude. So the magnitude of the peaks look a little bit off to me. So let's look on the next slide and try it. Let's look at it up. Okay, stretch it up. That fits better. So simple exercise, easy to do. There's no excuse not to do it. You don't want to just keep the geologic model so ingrained in your head that you're not willing to have an open mind. It's open mind with context. Okay. So now onto our big cell method. So in this picture, you have a bunch of smaller cells with variable dip bouncing around anywhere from 89.5 to 90.8. Sometimes you have to finagle the dip a little bit due to porpoising of the wellbore and small stratigraphic changes, and usually a combination of those things. So it's another reason to know your regional geology. So just little sidebar, because Jamie talked about it, you can't tell that much about faults from your horizontal well data. You can't tell reverse versus normal. You're not getting that kind of information from MWD, but I digress. Let's look at all these little cells in a big cell. Okay, that's a wrap. That same section of data, one big cell. It's all wrapping on itself about 3 times. So if we're getting a nice wrap, I can say I'm confident that the average formation dip, what the average formation dip is for this section. So it's just a good self check. And just a side note, sometimes this only works in areas, I also like to check this in areas where you have very minimal structure. You can always go back and kind of just make one big cell an area that you want to check and just see where you end up in that big cell and check it to where you ended up in your little cells and see that it's close to the same spot. Again, that only works in an area with minimal structure, relatively flat dip, places that rhyme with Permian. Okay. All right, next slide. So targeting. There are many methods. Their target changes are necessary. You want to get the maximum exposure of our producing interval, but unnecessary target changes can lead to microsteering, and that gives you porpoising, borehole tortuosity. You're going to have lower ROPs, lower end zone percentage, so your metrics aren't looking as good, and you're upsetting interteam problems. You're not making friends with your directional team. So it's a game of give and take in the lateral. You're kind of playing, I don't want to say games to make it light, but it's the games we play with the directional, with the DD. We're hedging our bets, and sometimes we make smaller drilling windows to give us a little bit of cushion from exiting. So just we have to think about, is it worth the dog leg severities, the changes we're making, or the lower ROP? And it's really important, just the number one thing, communication frequently and very specifically. You have to be preemptive with your communications. I'm expecting a dip change at this vertical section, and I'm likely going to send out a target change. You don't always have the luxury of doing that, but when you do, it's good. It's a good thing to do. And just think of the plan as a plan. As soon as we start drilling the well, we're starting to deviate from the plan. So that's all about that. So now just some examples of a target line change. So here, the target line, we're just drilling along, and it looks like the red cell, our last couple surveys, the formation dip's getting a little bit flatter. So the target line looks a little too steep for the dip. So on the next slide, we're gonna make our change. Okay, so we kind of flattened out our target line, and that looks a little bit better. So here we changed this. We just wrote out how we would write out the inclination. So it would be reported. We changed the line to 1230 TBD at 0 vertical section, 89.7. It's all projected back to 0 BS, the blue arrow. That's how we do our changes. Okay, so another way we do it. So that was by the line. We can also do targeting via window adjustments. So here we just have a basic window. We have 10 up, 10 down. Okay, so that's not working for us anymore because you can see the bottom of our window is out the target. So we're gonna make an adjustment at this point. So now a new window, we're just gonna shift everything up. We're gonna go 25 up, and we're gonna do 15 down. So we're just a little bit better. But the caveat to window adjustments is if your line is the wrong dip, here, if the dip remains flatter than the line, you're going to have to keep adjusting your window up. But sometimes that's better than trying to roll out a new plan. It's all based on the preference of your directional team and how quickly they can get a new plan out. All right. So, what's the most important thing here? Money. Having an economically beneficial well. We want the maximum exposure of the hydrocarbon producing strata. So the precision of our interpretation also matters to the output of our analytic projects. So small issues with well placement will just domino effect through your entire program. It can skew your understanding of your offset wells. It can mess up your future drilling and your completion parameters, which then affects your economics in your production. And also inaccurate geosteering, again, leads to suboptimal well economics. Your decreased drilling efficiency, you're not going to have as effective fracs and lower production. So it's important to always approach your geosteering interpretations with a geologic mindset. Our job is to make the best interpretation based on the available data. A good geosteerer is able to see different possibilities when you get new data, and you're having good intermediary communication between drilling and development. So you're just trying, we're trying to find a place where all of our goals meet. And I'm gonna hand it back to Jamie and see if we have any questions.
Great, thank you. As our questions are starting to come in, I want to remind everyone that later today you'll receive a link to a recording of today's webinar, an evaluation form, and a link to SCA's website with more information about how to register for geosteering best practices, pitfalls, and applied solutions for SCA. That's offered in Houston, Texas on April 10th and 11th and October 30th and 31st. So first question, what software do you typically use for geosteering?
So Sarah and I both, we mainly use StarSteer now. I've used Boresight in the past because I worked for Boresight BHL, but StarSteer is predominantly the top one now. We've also used ZoneView, a couple of much older ones. Sarah?
The original, I think we both learned on SES, which is pretty much a hyped up version of Excel. And then I've also used other softwares called another one called DynaView, but I think StarSteer right now is kind of the industry standard, what the majority of people use. We're not getting any kickbacks for saying that.
No worries. So are drilling engineers welcome to attend your class? Will they benefit for this? Or is this just for geoscientists?
I think it would probably help. Yeah, I think that'd be wonderful, and it would help with interdisciplinary, issues and concerns. Obviously we're consultants and we work with many different teams and companies, and when I find a drilling engineer that wants to actually ask the geologist and get the geologist's input, I think that's obviously the best case scenario. So sure, we would love to have engineers, and we'll try to pull back on the engineering jokes.
Oh, don't pull back. Don't pull any punches. What
Sarah,
practical approaches do you prefer while landing the well?
so just sort of what I went over with, previously with holding dip constant to know your dip, regional dip, the dip expected at landing. Hold that constant and shift the section rather than making extreme dip adjustments. And then, pre-drill work is so important for landing a well. If you have accurate structure map, make an accurate structure map. And that's where it all begins, is with your plan. Sarah?
Have all your, if it's not the first well on the pad, or even if it is, have all your closest offsets turned on in whatever in the software of your choosing. And a big part that Jamie harped on is having the closest pseudos, having closest verticals for direct comparison, and start with one big cell, keeping your dip constant, and then you can chunk it up into smaller cells to get a more precise, pretty looking picture.
Other than taking your class, how can people learn more about how geosteering is done?
You can get a software demo that usually comes with practice sets. And so that's certainly one approach, is to just get in there hands-on and play with some data and start. StarSteer, again, I'm not promoting a software here, but they have a pretty good online tutorial. They have lots of online tutorials for doing different things within StarSteer. So,
Excellent. Anything else you would add, Sarah? How did you learn geosteering?
I originally learned geosteering over Excel and SES. I wouldn't recommend doing it that way. But I think I hate to just keep saying StarSteer. I think it's kind of the Mac version of geosteering. It's very easy to understand, and I think it's good to just play with an entire well, a post-drill well, and then cover up the data and pretend like you're getting 90 feet at a time, so you can see what it's really like. That would be my biggest advice, because a lot of times when you're starting and it's your first day as an ops geo, they'll just throw you a bunch of wells to re-steer, and it's kind of not the same thing, because hindsight is 20/20. It's easy. You could just go to the end and see where where does that fit, rather than you have to think about, like the car example with Jamie's dog. You're only getting this much of data at a time, and you can't see where you've been.
And do you think there's opportunities for data analytics or machine learning to enhance the whole practice of geosteering?
That's a loaded question.
A loaded question.
Just say yes.
I'm sure there's room. Yes.
No, definitely, and can to even go further. And I know that it's already done. You combining that with your drilling data, and as you're drilling that data too.
Great. Well, that's about all the time we have for questions today. We're at the top of the hour, so we want to remind everyone that they'll get a link to the website with more information about registration for geosteering best practices, pitfalls, and applied solutions. That's offered April 10th through 11th in Houston, Texas. Thanks for joining us. Goodbye.
Thanks.
Thank you.